Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic we are going to give an introduction to algorithmic thinking. So in this topic, we will introduce the idea of a complete engineering problem. This is a description of the problem, requisite inputs, and the desired output. We will then also describe algorithms to solve these problems. Specifically, we're going to look at permutations and determining if a number is prime. We will then see that there are often multiple ways of solving the same problem, where some algorithms are better than others. Now, in secondary school, you were rewarded for solving problems. Most likely you learned by mimicking and/or repetition. Many students can factor a polynomial, but not that many could articulate the steps involved. There's a fewer number of students who can still calculate the GCD of two numbers, but still do not understand the steps involved to get to that solution. Give them two numbers, they'll find the GCD. Ask them to describe the problem. That may be a little bit too much. The issue is the reward structure. You were rewarded for getting the right answer. You were not rewarded for your thought process. Thus, when you were given a problem, you used the ideas you had in your mind and you used those to finally get to a solution. In engineering, we will define an engineering problem. That is a complete description of the problem, including requirements and constraints, and an explicit list of requisite inputs and the desired output. Now, larger problems generally are then broken into separate subproblems. Each subproblem is then solved independent of the others. So, for example, the input is given to subproblem is divided into subproblem A, which is then solved. The output of problem A becomes the input of problem B. Subproblem B is then solved. Its output becomes the input to subproblem C, which then produces the final output. Larger problems may see even the subproblems broken further. In some cases, inputs to larger problems may only be used for specific subproblems. In third and fourth year, you will also learn about feedback, where the output of one of the subsequent subproblems also becomes an input to one of the previous problems. Now, before you can solve a problem, you require a detailed description of the problem, and this may also be accompanied by requirements or constraints. Perhaps the solution can only cost a certain amount of money, or use a certain amount of power, or produce a certain amount of heat. And you may have other constraints as well. It must fit in within this limit. It must be way less than this amount, or some other constraint which cannot be exceeded. For example, in this topic, we're going to look specifically at four problems. Specifically, how many permutations of n unique objects are there? List all permutations of n given unique objects. Is a specific integer n prime? And we're also going to look at what seems to be a simple problem. Is m less than or equal to the square root of another number n? Next, once you have a description of the problem, then you also have to clearly specify what the inputs and outputs of the problem are. It may be a single value, like an integer, n. It may be a collection of n unique objects. If the problem is finding the shortest path from one location to another, the input may be the two locations, either specified by strings or perhaps by locations on a map. You may also want to avoid toll roads or major highways, in which case this may be two additional inputs to the problem, being true or false. Vital to are the units of any inputs and outputs under certain circumstances. So, for example, the Mars Climate Orbiter from 1999 failed. Why did it fail? Well, it failed to achieve orbit because the Lockheed computer produced output in pound force seconds. NASA was expecting the output in Newton seconds. The units were specified in the contract. The failure to adhere to the units resulted in the Mars orbiter failing to achieve orbit. Now, once the problem, inputs and outputs are given, one must ask, what are the tools we have to solve the problem? So as an engineer, you may be solving the problem with a computer program. For example, a software engineer will use a program to solve a mathematical problem. The tool is the programming language. An electrical engineer will use circuits. If you needed to build something, you might use a 3D printer, or you may purchase a microcontroller or other electronics off the shelf. And of course, there are many other techniques and tools you can use to solve various engineering problems, whether you're in civil, electrical, nanotechnology, or environmental engineering. Now, in your first programming course, you will be using a programming language as your tool to solve problems. The mechanism specifically will be a function. The inputs to a function are the parameters of that function, and the outputs will be return values. Additionally, for object-oriented programming, the inputs may include specific instances of data structures or objects, and the outputs may include specified changes to those objects. All right, so how are we going to solve some problems? Well, some problems can be solved through an algorithm. An algorithm is a description of a process for solving a problem through a sequence of well-defined, precise, and unambiguous instructions. In secondary school, you learned algorithms to solve very specific problems. But there was a problem there. You saw the teacher describe the algorithms, and then through mimicry, often you may have simply applied these algorithms yourself, perhaps correcting yourself until you got the correct answer. You likely did not consider what each individual step in the algorithm was. Rather, you learned simply how to solve a specific problem, almost if you were doing machine learning on your brain. For example, factoring or expanding a polynomial. You were given a problem, you solved it. In some cases, sometimes the inputs were even poorly defined. So for example, suppose you were describing an algorithm to a colleague, calculating the GCD. You can expect that individual to fill in the gaps, perhaps if you're not very precise or ambiguous in your statements. Also, 10 students describing the same algorithm will come up with 10 different descriptions. Unfortunately, in your first programming course, you must describe your algorithms to a computer in a programming language. And the computer expects very precise inputs and absolutely zero ambiguity in the instructions. If you incorrectly give the computer the wrong instructions, it will very quickly give you the wrong answer. The means by which instructions are given to a computer are through a well-specified programming language. And this, unlike English, does not allow for ambiguity. All right. Yes, you will see programming languages in the future. However, right now, let's first focus just on understanding the problems and the algorithms you've already seen in secondary school. And rather than solving these problems, you'll be asked to author algorithms to solve these problems. Algorithms which you have written down, which you can then pass to one of your peers, and they too should be able to solve the problems. Your target audience is going to be initially your colleagues, but by the time you get to your programming course, your target audience will be the computer and the requisite programming language. So for the rest of the talk, we're going to look at some problems and algorithms used to solve these problems. Finding the number of permutations of n unique objects, finding all permutations of n unique objects, determining if n is prime, and asking if one integer m is less than or equal to the square root of another integer n. So starting with the first one, given n distinct objects, what is the number of permutations of those objects? Well, the input is a non-negative integer n, the output is a non-negative integer n sub p, the number of permutations. Here's a very simple algorithm. We're going to call this algorithm number 1, and all we do is assign n sub p the value of n factorial. For example, there are 3 factorial or 6 permutations of 3 unique objects. There are 120 permutations of 5 unique objects. And for 525 unique objects, here we see the number of possible permutations. Alright, that's a very simple problem with a simple solution. Here, however, is a related but much more difficult problem. Given n distinct object, list all of the permutations of those objects. So the input is a non-negative integer n, and a list of those n distinct objects. The output is a list of lists of n distinct objects each. That is, the output includes all possible permutations of the n distinct objects. Assume that we are printing the first n letters of the alphabet. So we are now going to describe algorithm number 2. Start with a single list containing the letter A. There's only one permutation of one object, and that is our one permutation. If n is greater than 1, take the previous list and put B first before and then after it. Okay, so this produces both permutations of 2 letters. Now, if the number of objects is greater than 2, then we will carry on. For each of the previous 2 permutations, we will put the letter C first before the first character, then between the 2, and then after the second character. This produces 6 permutations of 3 letters. If the number of objects is greater than 3, then we will carry on by putting D first before the first letter, then between the first and the second, then between the second and the third, and then after the third letter of each of the permutations from the previous step. So this produces all 24 permutations of 4 letters. We could carry on this process. This is all 120 permutations of the letters A, B, C, D, and E. Now, algorithm 2 has some very nice characteristics. It's constructive. Given all permutations of k objects, you then build up all k plus 1 factorial permutations of k plus 1 objects. By the description, you can deduce that it works correctly. There is, however, one potential drawback. It requires you to keep track of all k factorial permutations at one step in order to produce the next k plus 1 factorial permutations. So let's look at a different algorithm. This is algorithm 3. So if n is equal to 1, just print out the list of the one object. If n is equal to 2, start with A and B, print that permutation, swap the first and second entries, and print this new permutation. If n is equal to 3, we will start with A, B, and C. We will print the permutation, swap the first 2 entries, print the new permutation, swap the first and the third entries, print that permutation, swap the first and second entries of that result, and print yet again the next permutation, swap the first and third entries, print the next permutation, and once again swap the first and second entries, and then print that permutation. That seems a little bit weird. Let's see how that works. Well, I start with ABC, swap the first two entries, and I get BAC. I swap the first and third entries, and I get CAB. Swap the first two entries, I get ACB. Swap the first and third, I get BCA. And swap the first two, I get CBA. These actually are all 6 permutations of those 3 letters. Now, we've seen the algorithm up until n equals 3. With n equals 4, we're going to do the following. We'll start with A, B, C, and D, but then we'll perform the previous algorithm for n equals 3 on the first 3 entries. This will produce 6 permutations of A, B, C, with D always being the last entry. We will then swap the first and fourth entries from the last permutation, and we will once again perform the steps for n equals 3 on the first 3 entries. Then we'll swap the second and fourth entries, perform the steps again for n equals 3 on the first 3 entries, producing the next 6 permutations, swap the third and fourth entries, and produce 6 more permutations. This produces a total of 24 permutations. So let's see how this works. We start with A, B, C, and D, swap the first two, swap the first and third, swap the first two, swap the first and third, swap the first two. Now we swap the first and the fourth entries. So now we have 6 permutations and a seed for the next operation. So swap the first two, swap the second two, first and third. Swap the first two, swap the first and third. Swap the first two. This produces the next 6 permutations. Now we swap the second and fourth entries. We repeat the process, starting with CADB. This produces the next 6 permutations, and finally we swap the last 2 entries, and we use that once again to perform the previous operation on the first 3. If you take a close look, yes, this actually does produce all 24 unique permutations, and all we did was perform swaps between each step. Okay, you might see a pattern here, but not yet. If n equals 5, we're going to start with A, B, C, D, and E. We're going to perform the previous algorithm on n equals 4 objects, producing 24 permutations, where E is the last entry, and then we will swap the first and fifth entries. Then we're going to do the same operation on the first 4, producing the next 24 entries, then swap the first and fifth. Previous algorithm again, swap the first and fifth. Previous algorithm again, swap the first and fifth. And finally, we will repeat the previous algorithm. So as you can see, this performs 24 times 5 permutations. Now, what is the pattern? Well, if n is odd, we perform the steps for n-1 entries on the first n-1 entries, a total of n times, and each time we swap between each of these, we swap the first and the last entries. But if n is even, we will perform the steps for n-1 entries on the first n-1 entries, a total of n times, but between doing these, we don't swap the first and last. Instead, first we swap the first and last. Between the next sequence, we swap the second and the last, then the third and last, and so on and so forth, up until we're swapping the last 2 entries. So because n5 is odd, we are always swapping the first and fifth entries. So suppose we perform all permutations of the first 4 entries of A, starting with A, B, C, D, and E. We then swap the first and last entries. Using that as a starting point, we perform the same operations finding all 24 permutations of the first 4 entries, always appending b to the end. Once again, we swap the first and last entries. We do this again and again and again, and this produces all 120 permutations of 5 objects. Because 6 is even, we go back to the alternate approach. Now, there is one serious aesthetic problem with algorithm 3. From the description, you have no clue if it actually works. But it has 2 incredible benefits. You only have to ever remember the most recent permutation of the objects and where you currently are in the algorithm. Recall the previous algorithm? We had to remember all n-1 factorial permutations of n-1 objects to create the n factorial permutations of n objects. This algorithm we just saw was proposed in 1963 by B.R. Heap. This is actually called Heap's algorithm, and it requires the least work of all possible known algorithms to produce all possible permutations. So you might be wondering, why do we care? Well, let's say you have an algorithm that has specific inputs and you want to make sure that your algorithm actually does work with all permutations of all possible inputs. This is an algorithm that will produce all possible inputs for you. Now we're going to look at the next problem, determining if an integer n is prime. Now, by definition, a number is prime if that number n is divisible by only 1 and itself. So the input is an integer n, the output is now a Boolean value. True if n is prime, false otherwise. Algorithm 4a. Try dividing n by each of the integers from 2 to n-1. If n divided by any of these values has a remainder of 0, then n is not prime. But wait a second. If m squared is greater than n, then if n is divisible by m, then n must be m times k, where k is less than m. So that means that if m squared is greater than n, then if n is actually m times some other k, then k must be less than m. So n must also be divisible by k. Now the proof is quite straightforward. If m squared is greater than n and n is equal to m times k, then assume that k is greater than or equal to m. But wait a second. If m squared is greater than n, it follows that m is greater than the square root of n. Thus, if k is greater than or equal to m, then k is greater than or equal to the square root of n. I have 2 inequalities. I can multiply both sides. Therefore, m times k is greater than the square root of n squared, which is equal to n. But this is a contradiction, as we assumed n was equal to m times k. Thus, k must be less than m. So now we have a different algorithm. Try dividing n by each integer from 2 up until the square root of n. This is significantly less work. So for example, if we wanted to determine if a number on the magnitude of 1 million was prime, we'd only have to divide it by integers from 2 to 1000. But wait a second. If m is divisible by m and m is composite, then n must also be divisible by any of m's divisors. Proof. If m is equal to the product of 2 other numbers, so it's composite, and n is equal to m times k, then n is equal to m1 times m2 times k. Thus, n is also equal to m1 times another integer. And also n is equal to m2 times another integer, so n must also be divisible by any divisors of m. Thus, if we are testing if n is divisible by a composite number, well, we've already tested previously its divisors, so there's actually no need to test if n is divisible by m. Thus, we have a new algorithm. Algorithm 4C. Try dividing n by each prime number from 2 up until the square root of n. Thus, we can determine if, for example, 9,991 is prime by trying to divide that number by all prime numbers from 2 to 99. Why is that? Because 99 squared is 9,801, that's less than 9,991, and 100 squared is equal to 10,000, which is greater than our target number. How do we know which numbers are prime? Well, you've memorized at least a few primes. You can probably guess if some other numbers are prime. But, well, we could try the following. We know that any multiple of 2 is not prime, so we could try dividing n by 2 and then by dividing n by all odd numbers starting with 3. There are also other tests to see if other numbers are composite. So let's look at this problem. Given an integer n, how do we know if the number is divisible by 2? That is, how do you check if n is a multiple of 2? The input is an integer n, and the output is a Boolean value, true or false. Here's a very simple algorithm. If the last digit of n in base 10 is divisible by 2, then n is divisible by 2. That is, n is divisible by 2 if its last digit is 0, 2, 4, 6, or 8. Well, here's another problem. Given an integer n, how do you know if that number is divisible by 5? So how do you check if n is a multiple of 5? Well, again, the input is n, an integer. The output is a Boolean value. Here's algorithm 5.5. If the last digit of n in base 10 is divisible by 5, then n itself is divisible by 5. So, for example, the last digit is either 0 or 5. Now, here's a third problem. Given an integer n, how do you know if the number is divisible by 3? Again, the input is an integer n, and the output will be a Boolean value, but you may have seen the following algorithm in secondary school. Given the integer n, we will assign it to a variable m. While m is not a single digit, we will assign m to be the sum of the previous digits of m. We will keep on doing this over and over again until m is only a single digit. Then n is divisible by 3 if m is divisible by 3, or if m is 0, 3, or 9. Algorithm 5.3 is a beautiful example of an algorithm that solves a problem but gives no insight as to why it's actually working. If some of you are interested, you might actually try to prove why this algorithm is indeed correct, and with the mathematics you know from secondary school, you should be able to prove this. But do that on your own time. As an example of these 3 different algorithms, let's see if this large number is divisible by 2, 5, or 3. Well, the last digit is not one of 0, 2, 4, 6, or 8, so this integer is not divisible by 2. The last digit is one of 0 or 5, therefore n is divisible by 5. And to see if it's divisible by 3, we will assign m to be the value of n. It's not a single digit, so we will add up all the digits of m. That produces 138. Well, 138 is not a single digit, so we will add up its digits. 1 plus 3 plus 8, that gives us 12. 12 is not a single digit, so we will add up its digits. 1 plus 2 is 3. Now we have a single digit, and m is one of those three values, 0, 3, or 9. Therefore, n itself is also divisible by 3. Thus, a potentially practical algorithm is the following. To test whether or not n is prime, try dividing n by 2, 3, and 5, and then continue successively dividing n by each successive odd number from 7 till the square root of n, where that number m is not divisible by 3 or 5. So, for example, we will not bother dividing by 15, 25, 27, etc. We will still be testing all prime numbers, but we will unfortunately test a few numbers that are indeed composite, such as, for example, 49. Now, this works well for small integers, but if n is on the magnitude of 1 million, this is actually going to result in having to perform several unnecessary long divisions to find the remainder. This is because there's only approximately 78,500 prime numbers less than 1 million. However, this algorithm would require us to still test over 250,000 numbers. Essentially, we would be performing 3.4 times more long divisions than the absolute minimum necessary. So instead, to ensure that we only use long division on prime numbers, we have to break the previous algorithm into two subproblems. The first subproblem is find all prime numbers less than or equal to the square root of n, and then, given this list of prime numbers, determine if n is prime. The result will then be a value either true or false. So, the problem is find all prime numbers less than or equal to capital N. The input is an integer capital N, and the output will be a list of integers. We are going to describe the sieve of Eratosthenes. This is an algorithm that has been known since at least 200 before the Common Era. We're just going to see how this algorithm works, but it's reasonably straightforward. List all the numbers from 2 until n. In this case, n is equal to 99. The first prime number is 2. We will then eliminate all multiples of 2 greater than or equal to 2 squared, which is 4. The next prime number is 3. We will now eliminate all multiples of 3 greater than or equal to 3 squared, which is 9. All right. The next prime number is 5, and we will eliminate all multiples of 5 greater than or equal to 5 squared, or 25. The next largest prime number is 7, and again we will eliminate all multiples of greater than or equal of multiples of 7 greater than or equal to 7 squared, or 49. Having done this, we observe that the next largest prime number is 11. But wait a second, 11 squared is 121. That's already greater than 99, and so actually we're done. All the remaining numbers that were not struck out are prime, and there's our list. Okay, so now we have all primes less than 99, and therefore we will now try dividing 9,991 by each of them. Here the remainder is 1, remainder is 1, the remainder is 1, the remainder is 2, the remainder is 3, remainder is 7. Carrying on, and on, and on, thus we get to the last prime number that is less than or equal to 9,991. That's 97. And dividing through by 97, we see that the remainder is 0. That is 9,991 is equal to 97 times 103, and therefore that number is not prime. Now, what was the point of those last few slides? Well, I hope you see by now that it's actually quite easy to find all the prime numbers less than or equal to the square root of 9,991 than it is to actually perform all the additional long divisions. The long divisions are the most amount of work, therefore it's easier to find all the primes first and then only divide through by those prime numbers. Now, for very, very large integers n, it's even impractical to execute the algorithm we just saw. So there are some algorithms that only give probabilistic results. If Fermat's primality test says a number is composite, it is. Unfortunately, it never guarantees that a number is prime. Just the more often you run the test, the smaller the probability that a number is not composite or prime. Now we're going to look at something that seems to be a lot easier. Is m less than or equal to the square root of n? That's the problem description. The input are two non-negative integers m and n, and the output is a Boolean value. So to solve this problem, which algorithm do you think is better? This algorithm, first approximate the square root of n using floating point numbers, and then test if m is less than or equal to that calculated square root. Algorithm 6b, test if m squared is less than or equal to n. So for example, if we wanted to test whether or not 59,232 is less than or equal to that given square root of that number, algorithm 6a would have you calculate the square root. You would then see that 59,232 is in fact greater than that calculated number, and therefore we would return false. Algorithm 6b calculates the square of 59,232, and then we observe that that squared number is greater than the given number n, and therefore once again we return false. The first algorithm requires you to do a numeric approximation. The second requires you to do an integer multiplication. Integer multiplication is a lot faster, and it is exact, whereas the square root is only an approximation. So consequently, you should determine that algorithm 6b is better than algorithm 6a, and much more preferable under almost all circumstances. And yet, students in second year seem to prefer to jump to methods such as algorithm 6a. So the point being here is there may be multiple algorithms that solve even the same simple problem, but some algorithms are simply better than others. Thus, in this topic, we have introduced the concept of a well-defined engineering problem. That is, we have a clear description of the problem, and later we will include requirements and constraints. We have specified inputs and expected outputs, possibly both with units. Now, there are some problems that can be solved through algorithms, that is, explicitly and well-defined sequences of steps which, if followed, will produce a solution. Algorithms may be simple or complex, elegant or brute force. Sometimes you may be able to see very quickly that an algorithm works. Other times, the algorithm may actually solve the problem, but there's no real hint as to why it does. We've also seen that there are multiple algorithms that may solve the same problem, and some algorithms are simply better than others. Do not ever assume your first algorithm you author is optimal, and don't assume the algorithms you've learned previously are optimal either. So, carrying on, we will look at other algorithms that you have seen in secondary school, but rather than you using those algorithms to solve problems, you will be asked to explicitly author those algorithms. Here are some references, acknowledgements, the colophon, and a disclaimer. Cheers!